Hey, Mr. Harridan here. It's been a while since I've done a video, so I'm going to do a video. I haven't done this one for a long time, so I'm going to redo this video about acids and bases here. We know that we see a lot of acids around us, mostly in food, like oranges have citric acid in it. Your stomach has hydrochloric acid in it. And then when we deal with our cleaners, those are usually bases, like drain cleaner is usually sodium hydroxide. So you need to know something about acids and bases here. So our basic definition of acids here, so this first definition right here is acid, is an aqueous solution that contains the H+. Meanwhile, bases is an aqueous solution containing the OH- ion, okay, which we should know is the hydroxide ion. Sometimes you will hear these called as alkali solutions, okay? There are some funky bases that do not have hydroxide in them. There are amine bases, okay? An example of an amine base is ammonia. Ammonia right here is the sneaky base. It's the sneaky base because the formula is NH3 and you don't see the OH in it. It's a sneaky base, which makes it weak, which we'll go over later, but that's okay. And then we are going to do the 3 definitions of acids. Okay? 3 guys came up with definitions for acid. The first guy was Arrhenius. He was the most basic guy here that gave us the definitions. Okay? He said an acid forms the hydronium ion in water. Now the hydronium ion is H3O+. Okay? How does the H3O+ ion form? Is when you take hydrogen and you add it to water. This is in equilibrium, which means these happen at equal rates, and you get H3O+. This reaction is in equilibrium. It is a reversible reaction. It goes back and forth all the time. Okay? So hydronium ion and the hydrogen ion are the same thing. Hydrogen ion, same thing as hydronium ion. Okay? Most of the time you'll see me refer to it as the H+ ion, but occasionally you'll see me do an H3O+ on you. Okay? So basically what Arrhenius said is acids contain H+. They produce H3O+. Bases form the hydroxide ion in water, which is OH-. Okay? So for instance, sodium hydroxide, it produces the hydroxide ion when it dissociates in water. Okay? And then acids, they produce the hydrogen ion when they dissociate in water, or they produce the H3O+ ion when they dissociate in water. Okay? I might be using the wrong term. Sometimes it's called this. I think it might be called ionization for acids and bases. I can't remember. I always get dissociation and ionization confused. Okay? I think ionization is for acids and bases. I think dissociation is for soluble ionics, but whatever. It's the same process. Okay. So that's your first most basic definition here. Okay. Unfortunately, the definition by Arrhenius doesn't take care of those sneaky, funky bases like ammonia. Okay. So then there's the Bronsted-Lowry definitions here. Those came next. Okay. He said that an acid is a substance that donates a proton. Okay. Which is an H+. Here we go. Good fun here. So if we're doing H+ here, okay, we know that the atomic number is 1, and we're going to pretend that the mass number is 1. if I do the protons, electrons, and neutrons for this, okay, this is the proton number, right? So we have one proton, because that's the atomic number. This is the mass number, which is protons plus neutrons, okay? So we would do 1 plus 0 is 1, so that is why we have 0 neutrons. I know. This is the charge right here, which is protons minus electrons, right? So this would be 1 minus 0 is plus 1 to do the charge. So there are no electrons. So what I'm telling you is the H plus is the same thing as a proton, which acids are proton donors. And remember, H plus is the same thing as H3O plus. They're all the same thing, okay? Because H pluses just don't exist by themselves. There's always in water. Okay, going on. Let's look at the Bronsted-Lowry base definition here. Okay, Bronsted-Lowry base. This is a substance that accepts a proton. See, Bronsted-Lowry, these are the proton dudes. He loved protons. So he decided, whoops, get on the page. He's the proton dude. He loved protons. So he decided, I'm going to make definitions of acids and bases based off of protons. So he said that an acid donates a proton and a base accepts a proton. Okay? That's what he said. And then, okay, Lewis. Oh, you gotta love Lewis, right? I love Lewis, of course, because he gave you Lewis dot structures, right? Remember where we did the little valence electrons, right? And we did oxygen and it had 6 dots around it. Yeah. Do you know who came up with that? Lewis, right? So Lewis, this is what's great about Lewis, okay? He's the electron dude, of course, because he made all his definitions based off of electrons, because he came up with Lewis dot structures. So he said an acid is a substance that accepts an electron pair. And he said a base is a substance that donates an electron pair. So in this example here, this is what they would call a coordinate covalent bond here. This is the electron pair that is being donated. Donated. Learn how to spell donated, Mr. Harridan. D-O-N-A-T-E-D. Donated. Okay? So, and this becomes the coordinate bond right here that gets shared. Which is all well and good. Okay? So, let me give you a little summary of the definitions right here. Okay? We are going to have an acid, and we are going to have a base definition here. Okay? Remember, acids have H plus, bases have OH minus. Okay? Okay. Try to make a table here, Mr. Harridan. Let's see if we can do this. So, so there's an Arrhenius definition. There's the Bronsted-Lowry definition. And there's the Lewis definition. Okay? Okay. So Arrhenius said acids make H plus, bases make OH minus. Okay? That is what Arrhenius said. Lowry, Bronston Lowry, remember that these are the proton guys, dudes. I should call them dudes. Proton dudes, right? So they said that these donate protons so the base accepts protons okay. Lewis is the electron guy, so his definitions are in reverse. So this accepts electrons and bases donate electrons, because protons and electrons have different charges. So it just depends on which way you're talking about. Okay, you guys are champions. The legend is out. And I appreciate those students being loud.